Good morning, everyone. I am Pubali Sarkar, Assistant Professor in the Department of Computer Science and Engineering. Today, I am excited to introduce our topic, Doubly linked list. In this presentation, we will explore what a doubly linked list is, how it works, and its applications. We'll cover the fundamental concepts, how it differs from other lists, and some practical examples. So, let's get started and dive into the fascinating world of doubly linked lists. Let's take a closer look at linked lists. A linked list is a type of data structure that allows us to store data dynamically, meaning we can add or remove elements easily without needing to resize arrays or move data around. This flexibility makes linked lists very efficient for managing data that changes frequently. Typically, a simple linked list starts with a null, which indicates the end of the list. Then, we have a header, which points to the first element in the list. From there, each element points to the next, creating a chain of nodes. This structure is really useful because it allows us to add or delete nodes quickly, especially at the beginning or the end, without shifting other data. Throughout this presentation, you'll see how linked lists form the foundation for many other complex data structures and algorithms. Let's talk about linked lists and some of their key features. First, there is a pointer called the header, which points to the first element or node in the list. This header acts like a starting point, allowing us to access all subsequent nodes. Next, each node is connected to the next one through pointers, forming a chain. The last element in this chain points to null, indicating the end of the list. One of the great advantages of linked lists is that they can grow or shrink dynamically during program execution. This means we can add or remove elements as needed, without worrying about fixed sizes. Additionally, the length of the linked list can be adjusted to match exactly what we require at any moment. This flexibility ensures we don't waste memory space, as the list uses only what it needs. Overall, these features make linked lists a very efficient and adaptable data structure for many applications. All right, let's walk through how we insert a node at any position in a doubly linked list. The first step is to traverse the list until we reach the node just before the position where we want to insert. So, if we're aiming for the nth position, we move to the N1 node, which we can call temp. This node is crucial because it's the point where we'll link our new node into the list. Once we've reached this node, the next step is to create a new node, which we call new node. We assign the data we want to store in this node to its data field. Remember, the key here is understanding that inserting at a specific position involves carefully navigating to the correct spot and then adjusting the pointers so everything remains connected properly. This process highlights the flexibility of doubly linked lists. They allow insertion anywhere, not just at the beginning or end. Connecting this to the overall theme, mastering these steps makes our data structures more dynamic and adaptable to different scenarios. Now, let's look at the next steps involved in inserting a new node at any position in a doubly linked list. In step 3, we need to connect the next address field of our new node with the node that is currently pointed to by the next address field of the temp node. This effectively links our new node to the node that comes after the temp node, maintaining the chain. Next, in step 4, we connect the previous address field of the new node with the temp node itself. This completes the bidirectional link, ensuring that both forward and backward navigation are properly maintained. These steps are crucial because they help us insert a node seamlessly, preserving the integrity of the doubly linked list. Understanding these pointer adjustments is key to mastering dynamic data structures, which are fundamental in efficient data management. Now, moving on to step 5, we need to check if temp next is not null. If it's not, that means there's a node following the current temp node. In that case, we need to connect the previous address field of the node pointed to by temp next to our new node. This step ensures that the backward link in the doubly linked list is correctly maintained, preserving the bidirectional nature of the data structure. Next, in step 6, we connect the next address field of the temp node to the new node. This effectively inserts our new node into the list at the desired position by linking it forward from temp. Together, these steps are crucial because they maintain the integrity of the list's links, both forward and backward, which is what makes a doubly linked list so flexible for insertion operations at any position. Remember, proper linking is key to avoiding broken lists or data loss. All right, so here we are at the final step, and as you can see, the doubly linked list now looks complete. What we've done is inserted the new node at the desired position, and as a result, the list has been correctly updated with all the previous connections maintained. This final structure shows how flexible and powerful the doubly linked list can be, especially when inserting at any position. Remember, the key takeaway here is that each node has links to both its previous and next nodes, which makes insertions and deletions at arbitrary positions more efficient. This example ties back to the overall theme of understanding how linked lists work dynamically and how their structure allows us to manipulate data efficiently. So, this final list is a perfect illustration of those concepts in action. Now, let's focus on how we can insert a node at any position within a doubly linked list. As you can see, we've included the necessary header files, stdio, h and stdlib, h, which are essential for input-output operations and dynamic memory management. In our structure definition, each node contains 3 parts: the data, a pointer to the previous node, and a pointer to the next node. This setup allows us to traverse both forwards and backwards through the list. In the main function, we initialize the head and last pointers to null, indicating that the list is initially empty. We then prompt the user to enter the total number of nodes, which we store in variable n. Next, we call createList, n, which is a function responsible for creating the doubly linked list with n nodes. After creating the list, we display it using displayList. This helps us verify that the list has been constructed correctly. The key part of this slide is how we handle inserting a new node at any position. We prompt the user to enter the position where they want to insert the new node, along with the data for that node. These inputs are stored in variables n and data. Then we call insertPosition, data n, a function designed to insert the new node at the specified position. This demonstrates the flexibility of doubly linked lists, as we can insert nodes not just at the beginning or end, but at any position in the list. Finally, we display the list again to show the updated structure after insertion. This entire process highlights the power of doubly linked lists for dynamic data management, especially when we need to insert nodes at arbitrary positions. Let's walk through this code for creating a doubly linked list with insertion at any position. The function is called createList, and it takes an integer n, which represents the number of nodes we want to create. First, we declare some variables: I for iteration, data to store user input, and a pointer new node for creating new nodes. We start by checking if n is at least 1, because if it's 0 or negative, there's no list to create. If n is valid, we allocate memory for the head node using malloc. Then, we prompt the user to enter data for the first node, read that input, and assign it to the head's data field. We also initialize the head's previous pointer to null because it's the first node, and the next pointer to null initially. Next, we set a pointer called last to keep track of the last node in the list, starting with the head. Now, we enter a loop that runs from 2 up to n to create the remaining nodes. Inside this loop, we allocate memory for a new node, prompt the user to enter data for the current node, and read that input. We then assign the data to the new node, set the new node's previous pointer to point to the last node, and set its next pointer to null. After that, we link the previous last node to the new node by setting last's next pointer to point to the new node. Then, we update last to be the new node, so it always points to the most recently added node. This way, we're effectively building the list step by step, linking each new node backwards and forwards as needed. Finally, once all nodes are created, we print a message indicating that the doubly linked list has been successfully created. This approach ensures that the list is properly linked in both directions, which is essential for efficient insertion and deletion at any position. Now, let's look at how we can insert a node at any position in a doubly linked list. Here, the function insertPosition takes 2 parameters, data and position. First, we declare pointers for the new node and a temporary node. If the list is empty, we display an error message indicating that the list is empty. Next, if the list isn't empty, we set temp to point to the head of the list. We check that temp is not null and then allocate memory for a new node. Once the new node is created, we assign the data to it. The key part is connecting the new node with its neighbors. We set the new node's next pointer to temp's next node, effectively linking it to the node that follows temp. Similarly, we connect the new node's previous pointer to temp, which links it back to the node before it. If temp's next node exists, we update that node's previous pointer to point to our new node, maintaining the bidirectional linkage. Then, we update temp's next pointer to point to the new node, completing the insertion at the desired position. Finally, we print a success message confirming the insertion. If, for some reason, temp was null, meaning the position was invalid, we display an error message. This process illustrates how doubly linked lists allow us to insert nodes at any position efficiently by updating multiple pointers, maintaining the integrity of the list. This flexibility is one of the key advantages of doubly linked lists in dynamic data management. Let's take a closer look at the displaylist function for our doubly linked list. This function's main purpose is to traverse the list and show us the data stored in each node. It starts by declaring a temporary pointer, temp, which we'll use to navigate through the list, and an integer n to keep track of the node number during traversal. First, it checks if the head of the list is null, meaning the list is empty. If so, it simply prints a message indicating that. Otherwise, it sets temp to point to the head node and prints a header message to indicate the start of the data display. Then, it enters a while loop that continues as long as temp is not null. Inside the loop, it prints the data contained in the current node, along with the node number. After printing, it increments n to reflect the next node and moves temp to the next node in the list by setting temp to temp next. This process continues until temp reaches null, which indicates we've reached the end of the list. Overall, this function is a straightforward way to visualize the contents of our doubly linked list, and it highlights the importance of proper traversal for understanding and debugging our data structures.